Hello again, folks. In this video, we'll be taking a break from learning about induction to learn about some useful Coq techniques. In particular, the idea that you can apply a theorem to arguments, just like you apply a function to argument, as a way of manually instantiating and specializing theorems. So let's look at the type of plus com real quick, just to get a sense for why this might be. There we go. It's a little big. So pluscom is a lemma that we have up top. It says that plus is commutative. It's a useful thing for any arithmetic reasoning. And you might notice that, oh, this for all, we've seen that for all before. It's the same syntax. In fact, it's exactly the same thing. Normally we've seen after the for all just a type. Here we have values of type nat just as well. Now it turns out that we can use function application, just like we do elsewhere, to specify the values here, which ends up being useful. So that's really hard to understand in the abstract. There's a bunch of text here that explains it in the abstract better than I'm going to do out loud. Let me show you in the concrete why you might care about this. So here's a lemma that has the sort of goal that you might end up caring about. You want to show some other commutativity result, that x plus y plus z quantity is the same as z plus y plus x, right? We're just reordering arithmetic. Now, this is the sort of thing that once you were introduced to the idea of commutativity in an algebra class, hopefully just felt like second nature, right? That you just sort of like, well, with pluses, you can freely rearrange the things that you're adding. Coq treats these things as plain symbols, right? It doesn't quite know that. So it's our job often to do some tedious rewriting to make things that are obvious to us obvious to Coq. Now, if you remember the pluscom theorem, this theorem isn't so hard. You might say, okay, yeah, okay, let x, y, and z be given. Let's rewrite with pluscom to start swapping it. All right, we're almost there. We just got to swap z and y. Let's do pluscom one more time. Wait, no. Oh, what happened? Wait, okay, let's slow down. Let's look at the left-hand side. X plus y plus z quantity, fine. Pluscom, okay, good. It switches, what exactly got switched? The y plus z and the x got switched, right? This quantity and the x got switched. So it's this plus that got sort of the arguments got swapped, right? I'll let you see that again yourselves. And the parentheses appear and disappear because of, the way Coq is going to treat associativity. This is a unit, and Coq wants to be left dissociative by default here. Now the problem is, in some sense, this is the outermost plus. So when you say pluscom, that's the first one Coq chooses to rewrite. So like, Coq, when you say rewrite, is going to find the first instance it can find. So that means sort of leftmost, outermost. That's how it's going to work. So there's a solution to this. Let me show you the plain solution first. The plain solution is to use an assert to control the rewrite a little more effectively. So okay, let x, y, and z be given, right? We're in the same proof state. Do the first rewrite, Coq picks the right thing. And now we're going to say, I want to turn this into this. So let me make an assert here, where now my goal is talking about this particular y plus z. Now there's like less noise, right? So Coq is not going to get confused when I say, okay, now rewrite by pluscom. Well, this is the leftmost to outermost plus, so it finds it correctly. Okay, and now we have a different theorem. So you might look at this H and say, well, that's the same as pluscom. It's like, well, it's the idea of pluscom, but specialized, right? Let's look at the difference. What is pluscom? Pluscom is for all n and m. So Coq's going to hunt around for the first thing it can find that will instantiate the n and the m. And it says, well, great, yeah, this will be my n and this will be my m, because this is the leftmost, outermost plus I could find. First instance works for me. But H, no, it only says for the given y plus z. So it's going to have to hunt, if we write from left to right, the default, it's going to have to find a y plus z somewhere. So it'll find the concrete ones we cared about and rewrite that correctly. This is like one of the many sort of like idiosyncrasies or quirks of Coq, where it's like, okay, you need to be this particular with it. Now, you might be annoyed by this, right? You might look at this and be like, this is a clunky way to go. I don't want to write stuff that way. That's a lot of crap to write. And like this distinction between quantified and concrete things seems complicated. I'm not happy about this. That's very fair. So the solution here is to explicitly apply. So let me show you. Let's get back to that same proof state, right, where we've done the first rewrite, and now we just want to swap these. So pluscom, if we look back at its type, says, okay, you give me an n and m, and then I'll give you a proof that n plus m is equal to m plus n. And then what we're going to say is, well, look, let m be y, and let n be z. You'll notice we don't need an @ sign here because these are not implicit arguments. These are explicit arguments to the theorem. Now, when we do that, that effectively does the same thing as this assert. It says, yeah, specialize this thing I'm rewriting by, specialize plus com to be y. Right, so this rewrite with this application amounts to all of the work we did right here. Right, so the idea here is if you have a theorem that starts with a for all, like plus com, excuse me, show me the plus com again, thank you. If you have a theorem that starts with a for all like this, you can apply that theorem to the given arguments you have there, and that'll give you more and more specialized theorems. Okay. Now, you can use theorems as functions this way, not just on for alls, also on arrows, and you can use them with many, many tactics. So here's another example. Here's a proof of transitivity. Right, let n and m be given, natural numbers, such that 47 equals n, and n equals m. We want to prove that 47 equals m. So you could do this with 2 rewrites, but maybe you look at transeq and you're like, yeah, I want to use transeq. But then you say, oh, apply transeq. And it says, well, I couldn't find an instance for the variable m. This is one of those circumstances where the name it's chosen is singularly unhelpful. Why did it say that? It couldn't find an instance for this variable m, the thing in the middle. So okay. That means what we need to do is we need to say apply transeq with n. Or, as I think I've taught you already, m equals n. If there's just one variable, you don't have to write the name. Say what you want it to be. So this is good. That's good. At that point, you don't need the parens. Right? And that's nice enough. You can also do it this way. You can say, look, I know what transeq is. Let's see it again. Transeq says you give me a type, 1 argument, and then 3 values, okay, total of 4 arguments. Then you give me a proof that n equals m, and a proof that m equals o, and then I'll give you a proof that n equals o. And what I'm saying here is underscore. Cock, you figure out these 4 things. What are they? The type, right? Okay, that's really going to be nat. Figure out the first thing, that's going to be 47. This is going to be n, this is going to be m. Now, I can write underscores for these because it's actually determined by hn, right? Hn says 47 equals n. This determines the first and second arguments and the type, right? Because, well, look, we have to be doing equalities on nats. The first one's 47, the second one's n. And then once I supply hnm, well, now I know what all 3 things are. So I can just write underscores. Right? Basically saying, cock, infer the things that I'm equating, but use these 2 equations. A helpful technique is you can run check on a compound expression and it'll tell you, like, look, this expression, and here now notice how it's writing what it inferred for us, is a proof that 47 is equal to m. Right? And if we like, we can do a partial application. Now here it does these existential variables, which we've seen before, where Cock doesn't quite know what it is, but it sort of is telling you, like, look, this is going to be a proof of n equals blah. I couldn't figure out that blah. And then 47 equals blah. Okay, well, we could plug something in here. Excuse me. And then now we get something a little clearer. So if you write these underscores and do partial applications, you might get that wonky output. Okay. Let's finish the proof here. Great. So the second example here, I want to show how you can do this with destruct. And that, I think, is actually a really nice way of working. So first I want to just specialize or be true if and only if to give us a convenient lemma that says, hey, if A or B equals true, then either A is true or B is true. Or be true if and if only if. Blah, blah, blah. Or be true if and only if does both of those. Yikes. Okay, so for this example, I want to show that, hey, if false or B equals true, then B equals true. Okay, so how's that going to work? Let B be given such that H, false or B equals true. So one way you can do this proof is you can say, well, hey, I've got that fact already. Let me find out, right? The conclusion here is an or. Let me supply, well, Cock, you figure out A, and then you figure out B, but then use H for this bit. which will be enough to tell us A and B, right? Because for A, H will say, oh, false or B equals true. So that means A will be false and B will be true. Excuse me, B will be B. Right? And now when we do this, let's first check the type of that, just to give you a sense of what's really going on there. Okay, let's do another one. Make it a little smaller so it all fits on one line. So here we can see the partial application saying, well, look, if you give me a proof that false or B equals true, then blah, blah, blah. Right, so this proof works. And then I say, okay, let's do cases on that or that was left. On the one hand, we have a contradictory case where we say false equals true, right? Because that's this branch, A equals true, but our A is false, so that's contradictory. Or in the alternative, B equals true. Now you might have noticed that there's a different way to do this proof. And you got me, right? That's you're not wrong. But this seemed like a simple enough setting for me to show you this destruct of not just a compound expression, but of a theorem where we say, hey, let me just look at the consequences here. This ends up being a really, really useful tool later on. In the next video, we're going to do a series of quizzes about just sort of this partial application thing so you can check your understanding. Once you have this tool, I think, and you get used to it, I think you'll become very, very fond of it and use it all the time. Okay, thanks. Talk to you all soon.